Welcome to a demonstration of the satellite mission use case of the OntoGrid project. We're considering plans generated by the ground segment and products generated by the satellite. On top here we see the plan files and below the product files. Any discrepancy between these indicates some problem with the operation of the satellite. A key technical step is extracting metadata from an implicit form, such as a file name, into an explicit form. This was done and an RDF representation of the data was generated. In this grid environment, the data is stored in one place, the generated RDF in another, and the querying happens from a third place. The user interface is deployed through a simple web browser, and here we see how we have generated some web forms to carry out commonly used queries. What we want to do here is find plan files that cover a certain period. So we select in this web form the date that we're interested in, and then the end date that we're interested in a few days later. And what this is going to do is tell us all the plan files that were generated by the mission planning facility that covered this time period. We can see them here along with their times. This can be carried forward to a second query where we're allowed to find out which instrument operations were planned. So we choose a particular instrument, the radar altimeter, and the user interface will tell us which events were planned, what orbit they were planned for, and so on. A third query that we generated a web form for looks at the product end of this. Comparing generated products with the planned events allows us to find out if the instrument has been behaving as is expected. This is the core of this particular part of the satellite mission use case. So we select the same time periods, we submit, and we get a set of products to compare with the planned events. We'll now look at a much more flexible free querying interface that was developed. This allows us to write queries directly in a number of RDF query languages. So we're generating one here. First of all, we declare a namespace prefix. Then we add in what we want to actually select. So we're interested here in plan file identifiers and two different times, the start and stop time for that plan file. We're in fact mirroring here exactly the first query that the web form was generating. This filter limits the timings that we're interested in. The numbers here actually represent seconds since the year 2000, which is a standard way to represent time in space missions. And we see here we found a single plan file covering the time period that we selected. So we now look at the second query we saw through the web form interface. What we're doing here is selecting the set of events and some associated information about the orbit and the duration of the orbit. But we're selecting the set of events where this particular plan file name is the one that we just selected, that we just saw. This is where we put in the various properties to say we want to select a set of events. We want for each of those events this event identifier, duration, orbit, and elapsed time. And we're filtering here on an event identifier only that features RA for the radar altimeter. And selecting this we see exactly as we saw through the web forms interface because it's the same query behind it. I'll now show how we can combine both of these queries into a single SPARQL query. So essentially what we do is combine the select and where and filter statements from both of them, so that we're allowed to query across, bridging the gap that was filled in by the copying of the file name from the result of one to the select of the other one. The key thing here is that using RDF we can chain together these queries based on properties and build up new queries iteratively. The final stage in this process could be a query such as this one, which would actually query across both plan files and product files. They're compared based on calculated times to see if the product times match up with the plan times, and event identifiers to see if they represent the operation of the same instrument. What we do is see if there is any product which matches up to a plan event file, and if there is such a thing, then in fact we're not interested in the results. So we'll filter out everywhere where there is such a product file, and what we're left with is any plan file for which there's no generated product, i.e. an instrument malfunction. Moving on now, I just want to show some of the flexibility in this approach of getting our information as RDF data and then querying it using these standard languages. So we've got here a simple query which gives us the start orbit for a particular product and also the originator of that product. I just want to show how we can elaborate on this sort of simple query to generate something that's more useful to an end user before we make it into a web form. So we're looking here at an RDF viewer called ISOVIS and a snippet of our product RDF information. So we've got selected here a single product file, and we can see that we have, for example, this orbit property which is a numeric property, as we can see in the middle there. Also, we have this originator property, which points to another RDF individual just here. And that itself has more properties, including one here, an originator ID, which is going to be more useful for our users to work with. So that's what we're going to select here. And adding those into our query and deleting out the intermediate stages means that we can have a query for originator IDs given absolute start orbits in a certain range, which is a helpful report for our users. I'm going to look more now at the semantic end of our work, in which we're trying to make sure we can talk about things in the language of the space domain. So we were selecting events based on them containing RA somewhere in the event identifier to indicate they were carried out by the radar altimeter. However, we can do somewhat better than this by moving to a higher level of abstraction. The query I'm writing here allows us to see all of the properties that we have for these events in order to see if there are any that will be more useful to select upon rather than simply this event identifier. So I'm asking for any property and for the name of that property and the value we have for that property for our event here, which will give us a full list of the properties attached to events. We can see here the usual ones we've seen before: event identifier, duration, orbit number, and so on. But also we see represents plan event here, which identifies another instance. Another way we could find out about this property is through an ontology viewer such as Neon here. As we go through looking at plan files, we see the usual properties. We can also then look across at these DMOP event records, the events that we're looking at, and we see again at the bottom here how we have represents plan event pointing us towards this object called a plan event, which is in fact, we can see here, a type of event. This query is selecting for that type of event plan event ID. So we've got the represents plan event property, and then we're saying that we want these plan event IDs and we want to filter on them. This is going to return the same set of events, but we've moved up a level of abstraction. So we're talking about types of event, seen on the right here, rather than specific event identifiers contained in file names. We can, in fact, be more specific here and list the exact event identifiers we're interested in, rather than having to rely on this filtering on a regular expression. We can actually go even further than this. As we look back at the ontology, we can see for every event type here, we have an executed by instrument property. And in fact, instruments have their own identifiers, and this is really the level at which scientists are going to want to be talking about the satellites. So we can replace our selection of a plan event identifier by saying for every event type, we're just interested in which instrument it was executed by. And in fact, we're interested only when that instrument is radar altimeter. So we've moved our query from the implicit world of looking at particular event identifiers up to the explicit world of talking about instruments themselves. And if we just change here the two letters to go from the radar altimeter to a separate instrument, our query is changed to pick up a whole different set of events linked by the same property. We can see here even one of them does not have the same sort of identifier as the other ones, but we've still found it through this more semantic query. The final thing I want to show in this demonstration is one of the advantages of the abstraction of components in this project. So far we've been using SPARQL as our query language, but we can see here a query in a separate language called SPARQL. Nothing has to change in the underlying components or the annotation or the data. We can just swap in a different front end to the query which accepts SPARQL as its query language instead of SPARQL. I'm going to frame my analysis of this approach using SOCU's service-oriented knowledge utilities. The system works to integrate data from many different sites and can also make updates to those data, for example if a plan file replaces an older plan file. We can't predict ahead of time what sorts of queries will ultimately be useful, so we need to have a flexible interface to explore the data that we have. Abstraction of data allows us to have flexibility and easier migration paths. Abstraction of components means we can take advantage of developments elsewhere and incrementally improve our system. This approach has mined implicit metadata and made it explicit. This has given us clarity both for end users and during development. So to summarize, we have virtualization of the data in an extensible system with very low barriers for uptake, and we've enabled effective collaboration between experts and built a system that scales. What this means from a business perspective is we can replace expensive purpose-built systems with new flexible interfaces that allow experts to explore combined legacy and new data in semantically meaningful ways.